Okay, so after finish the potential that we start to talk about the barrier tunneling. Barrier tunneling. So here you can see a plug 就是那个曲棍球的那个球就是 slide over the frictionless ice towards a hill. The plug's gravitational potential at the top of the hill will be UB. So now we consider the gravitational potential. And similarly, the gravitational potential is similar to the electric potential, which we will talk about later. And in classical mechanics, so this is UB, and this should be mgh. Mgh will be the mass of this plug is m. And then if this plug need to get through this small hill, then the initial kinetic energy 1/2 mv squared must be larger than UB. If you consider there is no friction, no force between the plug and the ground. You need to assume there is no frictional force. Then K must be larger than UB, because if the plug go to here, if KB is larger than UB, then part of the kinetic energy transfer to potential energy, and there is still remain some of the kinetic energy, so the plug can go through. If K is smaller than UB, then maybe it just go to up to here. Then here all the kinetic energy has already transferred to potential energy. Then it can only go back. So this is for classical mechanic case, and in quantum mechanics it is the other way around. This particle may have some probability to go through this so-called barrier. So we have the barrier tunneling effect. In Chinese, we call it 串隧效应. Tunneling effect. So as the plug climbs the hill, kinetic energy transforms into gravitational potential energy. If the plug reaches the top, its potential energy is UB, thus the plug can pass over the top only if its inertial mechanical energy E is larger than UB. Just mentioned it. So the hill acts as a potential energy barrier, or for short, a potential barrier. Okay, so here we have a different setting. Rather than the previous case, we only have the first two segments. Now we have the third one. So for the first and third one, we have V equals to 0, and in the middle one, we still have VB smaller than 0. So in this case, the potential barrier is like this. 0 in region 1 and region 3, and then UB in region 2. And VB is negative, so E times VB is positive, UB is positive here. So there is a potential barrier for a non-relativistic electron traveling along an idealized wire of negligible thickness. The electron of the mechanical energy E approaches a region barrier in which the electric potential VB is negative. Okay, so just mention. So the electron being negative charge, we have a positive potential energy because UB equals QVB. In that region, if E is larger than UB, we expect the electron to pass through the barrier, as in the classical mechanics, and come out to the right. If E is smaller than UB, we expect the electron to be unable to pass through the barrier region. This is the concept, this is the intuition in classical mechanics. but not for quantum mechanics here. So some astounding can happen to the electron when E is smaller than UB. Since it is a matter wave, the electron has a finite probability of leaking, 就是漏掉的一个几率or tunneling 串过的那个几率 through the barrier and materializing on the other side. 它就是穿过那个位能的墙穿墙串到对面去。So moving rightwards with energy E as though nothing had happened in the region. Pretend nothing had happened. Okay. So the wave function phi x described the electron can be found by solving Schrodinger's equation separately for 3 regions, similar to previous case. The previous case only have 2 regions, region 1, region 2. Here we have also region 3, which has the potential to be 0. So the first region is to the left of the barrier, the region 2 is within the barrier, and the region 3 is to the right of the barrier. So the arbitrary constant that appear in the solution can be chosen so that the values phi x and its derivative with respect to x join smoothly, which means continuous for the wave function and for its derivative. At x equals 0, this is the boundary between region 1 and region 2. And at x equals L, which is the boundary between region 2 and region 3. So squaring the absolute value of phi x, which is the wave function. So we take the absolute value and then square, which is the probability density function. Then yield the probability density. Okay. So here we try to solve the Schrodinger's equation for the tunneling effect. So this is region 1, region 2, region 3, as I just mentioned. So for region 1, we have U equals 0 here. And then, so this is actually the same as the previous case. So I don't try to repeat it again. I just assume K to be this term, and then we have the solution to be like this. Because actually there was some probability that the electron can be reflected by this wall. So we have both the positive and negative terms here. So we have A times this one and B times this one. In region 2, similar to the previous case, we have U equals UB. And then, but here, we need to remark that E is smaller than UB rather than E is larger than UB here. So we need to be cautious about this case, because here we have a d2 phi dx2 plus, I should write it as a minus 2m and then ub minus e all over h bar square, and then phi equals 0. Why I need to write it like this? Because here we have ub larger than e, so I write it here ub minus e. This one is a positive value, so we have a negative sign in the front. Okay, so in this case we should assume b to be the square root value of this one, because this term is positive value, so we can take the square root of this one. We get 2m multiplied by ub minus e, not e minus ub anymore. So we have this square root term and then over h bar. So this one becomes d2 phi dx2 minus b square phi equals 0, like this. So if you try to solve this one, you have s square minus b square equals 0. So s equals plus or minus b. So we don't have I here. This is positive. This is real solution, distinct real solution. S equals plus or minus B rather than J times something. So we have a C times exponential to Bx plus D times exponential to negative Bx, like this. So you need to pay attention to these two terms. Okay, for region 3, which is similar to that one, we have E minus 0. And then originally we should have E times this term plus F times exponential to negative ikx, but we also suppose that the electron is coming from the left side to the right side, so on the region 3 we don't expect it is refracted by anything else, so it only goes to the right side in the region 3. So we have phi 3 of x equals E times exponential to ikx without the negative exponent term, like this. Okay, so we have phi 1, phi 2, phi 3 for the region 1, region 2, region 3. Okay, so actually we need to determine the coefficient. And of course, now we have phi 1 of x equals a times exponential to ikx plus b times exponential to negative ikx, and then phi 2x is c times exponential to bx plus d times exponential to negative bx, and then phi 3 of x is e times exponential to ikx. So for the first one, we have x is smaller or equal to 0, and then for the second one we have 0 is less than or equal to x is less than or equal to L, and then for the third one we have x is larger than or equal to L. So we still have some boundary conditions. Okay, in short form we may write it as a BC. So we should have, for the boundary here, so this is region 1, region 2, region 3, this is 0, this is L. Okay, so we should have phi 1 of 0 equals phi 2 of 0. This is the first boundary condition at here. And then we also have phi 1 prime of 0 equals phi 2 prime of 0 here. And then the next one is here as x equals L. So we will have phi 2 of L equals phi 3 of L. And then we also have phi 2 prime of L equals phi 3 prime of L. Okay, to solve it will be complicated. We need to do some approximation. So you can see actually it has some approximation here. It does not take the equal sign. It is approximately equal to that value. Because when you try to solve this, actually I can try to write something out so you can see. For the first one, it is still easy. It is nothing but a plus b equals c plus d. And then for the second one, we have ak plus ak minus bk equals cb minus db. Yeah, this two is still okay because we plug in 0 there. So exponential to 0 is only 1. But here we have something more complicated. So it will be like c times exponential to b capital L equals, plus d exponential to negative b times capital L equals e times exponential to ik capital L. Well, to solve it will be more complicated. And then still this one, we need to take the derivative. So we will have c times b exponential to b times L minus d times b exponential to negative b times capital L equals exponential to I suppose I should have I here. I should have I here because the I cannot be cancelled. The I cannot be cancelled because this is a this is a real function. We don't have I there. So here we still have I times k and then exponential to ikl. So you can simply imagine that to solve this 4-joint equation will be quite tedious. But hopefully we can do some approximation. We just assume that this one should be very, very small. This one should be very, very small, which will be like, because for this one we have something like a exponential to ikx plus b times exponential to negative ikx. And at least we know this is a real function. And it is continuous here. So this turns out to be a real function, which means that a and b should be complex conjugate to each other. And it finally is a standing wave there. It's a standing wave. And then as much as the probability of the particle to go through this wall should be small, it shouldn't be like something, should be something like this. It shouldn't be something like this. Otherwise, it feels like it has a high probability to go through. And actually, you can see, as much as the first derivative is continuous, which is like on the left side. This is the derivative on the left side, and the derivative on the right side should be continuous, so that you can see it's something like that, not something like that. This is not okay. This is not continuous for the first derivative. This is continuous for the first derivative and also for the wave function itself. Actually, this is the probability density function. So we already take the absolute value square. So this is a standing wave here, and then this is an exponential decay. Because here we only assume that c is small. Assume c is small because for this term with x is larger, then this is exponentially growth, and for this one this is exponentially decay. So we will assume that this one the c should be small. So the probability that the particle should be able to go through this potential barrier is that the wave function at L over the wave function of 2 at 0, and then this quotient take the absolute value and then square. This is the probability that the particle can go through this potential barrier. And it will be, if we assume that c is small and then we just ignore this term, then this is nothing but exponential to minus bl and then exponential to negative b0, because we just plug in l and 0 to here and then just ignore the first term. So most of the thing can, this d can be cancel each other. So actually we don't really need to solve this joint equation if we make this approximation. Then the complicated things we just skip through the complicated things. So the final value, the final solution will be this one over this one, and exponential to 0 is nothing but 1, so this is exponential to negative 2bl. So this one take the square is 2 times bl. So this is the probability that the particle can go through. And you can see that the probability related to the thickness of the wall. If you still remember, L is the thickness. So if the wall is thin enough, then the particle is more probable to go through. And this is B. So if now we know that E is smaller than UB, but if E is close to UB, then this term will be smaller. We'll also make this term larger because exponential to negative something. If B is smaller, this term will be larger, which means that even though if the kinetic energy is smaller than the top of the potential wall, but if the kinetic energy is close enough, then the probability of the particle to go through this wall will be larger. Okay. So this is the interesting stuff here. The tunneling effect. Okay, so actually we use this effect for the microscope， 就是这个叫做 tunneling microscope 串穗式显微镜，scanning tunneling microscope。那你们可能在中学生物堂的时候用过一些很旧的那种很低阶的显微镜的话，是那种光学的，纯粹用镜子的折射来放大。那高一阶的话可能是电子显微镜，那再高阶的话就是用那个串穗效应去做这种很高精度的那种放大的效果。So so I actually don't know what is, but it can actually try to observe the particle pattern, the pattern of the particle, something like that. So it try to move the tip close to the surface. You try to observe, and then of course you should be able to know what the material is, and so this gap is like the potential wall. So you can try to count how many percentage of the electron can go through this potential wall. Then you know for this coordinate what is the distance between the tip and the surface. So you just try to scan through the surface. You are not actually watching the particle itself. You try to observe how many percentage of the current can go through this potential wall, and then you use this to derive what is the distance. So you know, here this particle is lower, for that one the particle is higher, then you know the distance. Then you can try to use this phenomenon to reconstruct the image of the pattern. Yeah, that's okay. So let's see a sample problem here to finish off this chapter. Okay, so here it says, suppose that the electron have a total energy E of 5.1 eV, 5.1 eV, approaches a barrier of height UB to be 6.8 eV, and the thickness is L. What is the approximate probability of the electron can be transmitted through the barrier to appear on the other side of the barrier? Okay. So yeah, so actually we can just use the equation we just derived. So B is nothing but 2m and then UB minus E, and then square root all over h bar. Okay, so UB is nothing but 6.8 eV, E is 5.1 eV. So we just need to put in all the values. So 2 times m is 9.11 times 10 to minus 31, and then times this is 6.8 minus 5.1, and then multiply by 1.6 times 10 to minus 19. And then this one we should take the square root, and then all over reduce Planck constant, which is 6.63 times 10 to minus 34 over 2 pi. Okay, so here B is 6.67 times 10 to the 9th power, and then the SI unit should be meter inverse. So if you just look at here, this is exponential function. The exponent should be dimensionless, and then L is the length. So B should be the inverse of length, should have the dimension of inverse of length. So B has a SI unit of meter inverse. Okay, so the probability of the tunneling is actually T equals exponential to negative 2B capital L. Okay, so we just need to plug in the value. So we have exponential to minus 2 times 6.67 times 10 to the 9th power, and then multiply by 750 times. This is picometer. Pico is 10 to minus 12. 10 to minus 12. Nano is 10 to minus 9. 10 to minus 9. Okay, so this is actually 45 times 10 to minus 6. 10 to minus 6. Which means for a million of electron, 45 can go through. 45 can go through. 45 out of a million electron can go through. Okay, this should be B. This should be B. So what is the approximate probability of that a proton with the same total energy will be transmitted through the barrier to appear to the right side? So the question is actually the same. All the numbers are the same. The only difference is that we change the electron to a proton. So this is not electron anymore. This is proton. This is proton. So actually we need to calculate the B again. This is 2m UB minus E, and then square root of it, and then over h bar. So this is 2 times the mass of a proton is much heavier than the electron. So this is 1.67 times 10 to minus 27 power, and then times still 6.8 minus 5.1, and then multiply by 1.6 times 10 to minus 19, and then the square root of the whole term all over the reduced Planck constant, 6.63 times 10 to minus 34 over 2 pi. So this B is much larger, 2.86 times 10 to the 11 power meter inverse. This is much larger, so the probability will be even smaller. So actually t equals exponential to negative 2b capital L. So exponential to negative 2 times 2.86 times 10 to the 11th power, and then still multiply by the 750 picometer, 750 times 10 to minus 12. So you can see, this is much larger. Wow. Oh. This is 8.3 times 10 to negative 187. Oh. Okay, I don't know how to call this one. Yeah. This is a really small, really small. And you can simply imagine, even we change it from electron to proton, the probability of tunneling it decreased drastically. Here, for a billion of electron, there are still 45 electron can go through, but here, I don't know how to say. Oh, this is 10 to the 187 power. Only 8.3. So this is really small, really small. I don't know, you need to win how many times you win the lottery consecutively, then you get this probability. But this is a really small. So you can imagine that. So you may say sometimes I just mentioned something. Someone may say you still have probability to go through the raw, but the probability is even much smaller than this one. Maybe 10 to negative 10,000 power to go through a raw. So don't try to do that. Okay, so now we